All right, everybody, we're going to get ready for our afternoon session now. So our next speaker is going to be Shukla Poddar, and she's going to be talking about your data sources and their applicability for studying energy metrics. So thank you, Shukla.
Thank you, Melindy. Once again, thank you, and I hope you enjoyed the lunch. There's so much more left. So in case you're hungry in between, or you just want to have a little snack, so feel free, and we can still continue talking about the data and the data sources, but making it more enjoyable with the little nibbles here and there. So before I start presenting, I just wanted to give a little bit of introduction of about who I am and what do I do and why do I care about data and climate and energy in specific. So I was a PhD student with Melindy and another supervisor, Jason, who is from the Climate Change Center, which was a bridging gap between understanding climate change and the renewable energy industry, actually. From there, after my post-PhD, we have kind of spoken to a few of the industry partners in this space who use a lot of data and modeling and the approaches that they have been using. And what we came to know was not a lot of people or not a lot of industry personnel who use this sort of data. They're actually aware of the vast data sources that we have, and most importantly, the free data sources that we have. So which was a major motivation and driving force for organizing this workshop. And also we wanted the two different sets of world to actually talk to each other, the climate people and the renewable energy people, and understand the synergy that we have in these two different worlds, which is actually very important if we want to achieve that net zero sometime in the near future. I'm not saying the number, but hopefully very soon. So I just wanted to start with showing the existing renewable energy scenario in Australia and where we are actually heading towards in the future. So we have quite a few solar and onshore wind kind of all stacked together near the New South Wales and Victoria, and some sparsely distributed here and there over Queensland and Western Australia. But if we actually look into the proposed one, you can just see huge chunks of yellow blobs all across the eastern coast of Australia. And also a lot of pumped storage in the future. Also to highlight the onshore and the offshore wind, which is also going to take a huge part in the renewable energy industry in the near future. And then at the bottom, I have just put the location of the network, which is the main driving reason why we see that huge blob of yellow and green all around the eastern coast, but also highlighting the two large-scale projects, the New England Solar Farm, which is one of the largest solar project for the New South Wales, and the Sun Cable up there in the Northern Territory. Having said that, I think last year it was Ausgrid's report that they highlighted how many customer outages that they had. So they basically, in this report, they had filtered out all the network outages that they saw less than 3 minutes. And then they did a huge calculation spanning from the financial year 2012 onwards till 2021. And we could see the frequency of the huge frequency of the events, and also the customer minutes that were interrupted because of these outages were noticeably large for 2015 because of a huge storm that had impacted, and then 2019, 2020, which we had bushfires, then followed by some storms. And what they basically saw that 27% of these events were just weather related. It's nothing to do with the what was happening with the operations part of it. And this resulted in 66% of the outage minutes that the customers actually experienced. And a major thing that came out of that report was they had not considered anything that was related to the climate or the weather events that were taking place, and which resulted in this huge blobs in 2015 and 2019-2020 period, which they were overlooking. Then to go on to why do we need the right kind of meteorological data. So I'm just going to put few important things that we look at with this meteorological data, or the current challenges that the industry is facing. First and foremost being the intermittency issue. Solar being highly unstable, anything with a small resolution, anything with a time scale of like 1 second to even 10 minutes of clouds passing, it could just cause huge amount of ramps, and which is heavily reflected on the amount of power generated. Then we have a major growing issue of curtailment. Interesting and a nice duck curve, which is being referred to every now and then now, and that's because we have too much solar coming in the middle of the day, leading to this increasing issue. Then again, another thing, that's capacity uncertainty, because a lot of these renewable energy resources is just heavily dependent on the local weather and climate conditions, and sometimes a sudden change can lead to unaccountability of in this capacity calculations. And then not to forget climate change, which is slow but steadily progressing. We have already reached the threshold of 1.1 degrees Celsius, and we are expecting at least 3 to 4 degrees Celsius rise in the temperature than what we are, if we keep on continuing the same trajectory of emissions that we are doing at the minute. But also, we need the right kind of data for a lot of other important things like predictive maintenance, for extreme weather assessments, and what is the impact of the extreme weather that has happened. Especially for mitigation, a lot of the data is required for operation and maintenance of the large-scale solar and wind farms, and optimizing generation, understanding the fault detections, and if we can have a system that can detect early fault detection, which Earl was mentioning in the panel today. So having said that, this is a very interesting figure which I found from a recent workshop that was actually organized, and they were also kind of talking about why do we need a synergistic and a holistic approach in terms of weather and climate scientists and renewable energy modelers. So basically what climate scientists would be more interested in are the occurrence of these certain events, or why it has occurred. So, for example, it could be a tropical windstorm, or could be heat waves, floods, droughts, or what is the compounding event that has occurred, like heat waves followed with bushfires, for example. But for the energy industry, it would be what is the impact of any of these events that has happened, or what is the cascading impact that it can have, that can occur to the generation side of it, or to the consumer aspect of it. So basically, all the different weather phenomenon could be directly or indirectly related to some of the major issues that we are actually seeing in the renewable energy industry, like curtailment, the energy and generation constraints, even the storage constraint, and what would be the changing system costs, and even the dynamic prices in the energy market. So moving on to using weather and climate data for energy estimations. So I'm just going to brief you about why do we need to distinguish between climate and weather. So weather is something that describes only a short-term condition, and just responsible, some of the weather variables responsible for a given region. But when we look into a longer period of time, like let's say 20 or 30 years, it is what your general climate is going to give you a view about. So if we are looking into something very short term, or we are looking into something that has happened probably yesterday, maybe we would go back and refer to what was the weather yesterday. For example, last 2 days back, Sydney had extremely hot temperatures, like 38 degrees Celsius. Suddenly it started being very windy through the afternoon. So if we wanted to understand what was the impact of it on the generation side of it, we would be going and looking back only at that day's or even the particular hour's data set. But if you want to look at general overview of what would be the generation for Sydney in October, let's say. So we would look at a longer term average of data set that's 30 years or 25 years, at least 25 years of data. And that's why climate is very important. So for the renewable energy industry, we kind of need both. We need weather as well as we need climate, but it just depends on the context of what we are using it for. So again, as I mentioned, we would use the climate if you're looking at the long historical averages, or if you're interested in understanding what is the steady state condition of that location or that region of that country. But if we just are interested in what was it yesterday or what was it 10 days back, so we just look at that shorter time scale kind of thing. But interestingly, the thing that we use in the energy industry, which is very common not only in Australia but also globally, is something called the typical meteorological year or TMY. People using PVSystem or some other sorts of software would basically go for a TMY file. And TMY file is good in order to get a general overview of what's happening in the energy market, how it is reflecting, but it wouldn't capture all that variability. That's just because it doesn't, so the way it is calculated. So for example, if you have 20 years of data, so it might pick what would be the median of that 20 years of data. So if the January could be from some year, your February could be representative of a different year, and it creates a whole 12-month period based on this method of randomly selecting your data. So again, in that sense, so if you have irradiance and if you have temperature, they might not be of the same year and the same month sometimes. So when you actually trying to talk about how your temperature was impacting your load generation and how your irradiance was impacting your PV generation, it might not be the two same things or the same years that you're actually talking about. So again, it creates a lot of big gap and discrepancy. So and to give a small example, so we recently did some work with a company, a large-scale solar farm in the Middle East. They got their estimates from a big company. I'm not going to reveal the name. And they were just seeing that they were 15% off from what they were supposed to generate. And that was the reason because they went ahead doing all this estimation before setting up the project with a wrong reference year. They just randomly chose the year which was the best performing year, and then that 15% losses was too much for them. They had it for 2-3 years and they just went on. They were trying to send some of the panels to see if the modules had failed because of the desert conditions, but it turned out that the modeling approach was not correct, because of which they saw that massive difference, and the modules were fine at the end.
Quick question on this. So we don't do this because we're also really worried about coincident wind in a localized region with solar as well. So if you're taking this approach, you risk getting a mismatch between wind and solar. So is the industry going away from this type of approach, and just running bigger data sets?
So we would love that the industry goes away from that approach, but not a lot of industry take that approach unless they have had some past experiences where they have lost billions of dollars in some case or the other. So like the example just that I mentioned right now about the company, the large-scale solar farm in the Middle East. So they had the plan in Jordan, and they were seeing like massive reductions in whatever they had projected financially. They just couldn't see that because the generation was approximately 15% low. And they did back and forth, going back to the company who had given them estimates, and they pointed out maybe the modules were not performing. So at the end, it was the manufacturer's fault, according to them. So there was this whole thing here. But that's very good to know that you guys have moved on from that approach and looking into more correlated data sets so that you can account for that variability that's happening around. Okay. So the data types. So we basically have the three different types of data types, basically based on which period that you want to look at. Looking into the past, it would be the observations, which comes from weather stations, buoys, a lot of radars, even satellite data. Then there is reanalysis, which is a very good example of a high spatial and a temporal resolution data, which is kind of assimilated with all these observations and also run with some satellite data and models. And then climate models, which have the ability to predict a whole range of possible future scenarios and also take into account what has happened in the past, looking back into like 200 or 300 years, and again till the end of the century for the future period. So I'll go one by one on the different data types and what is out there and what we can use. Okay, so this figure is kind of similar to what Melindy showed in her presentation, but I'm just going to take you through it again. So basically for observation systems, we have either we have measurements, and these measurements could be either direct or indirect. So when we are talking about direct measurements, we have sensors that would be giving you those sorts of values. So let's say there is a pyranometer giving you irradiance data. But in terms of indirect observations, that could be derived from ice cores or tree rings, which is not that much useful for the renewable energy industry, but that is also another type of observation data that's being collected, and huge part of it was NOAA, funded by the US government, which is having a bit of issues right now to continue whatever they were doing. But they have this vast majority of data sets that they have collected in the past, all quality controlled and maintained very nicely. So in terms of the observations, we can have the buoys, also some weather ships, radars, aircrafts, geostationary satellites, the polar orbiting satellites, and again some ground-based monitoring stations or surface or the sensors attached to them. And in terms of the reanalysis, so reanalysis is high spatio-temporal resolution data that is produced by combining the numerical models along with the observations. So basically, they take in a bunch of observations coming in from the figure that I showed before. So they would just do all sort of data assimilation from weather stations, buoys, radars, and then they have their own numerical models like a CMWF model, which resolves the grid of the Earth into what is exactly happening. So they would have a radiative transfer budget, then calculating all the heat exchanges, and basically segregating or subdividing the Earth into smaller pixels and representing what is exactly representative of the local climate conditions at that grid. And this data, again, this data estimate spans for a longer period of time. So most of the reanalysis data sets, they are available from 1970 onwards or 79 onwards. And again, this is an older figure, so it stops at 2010, but we have it continuing till 2025, and it gets updated every month or every year, whatever, based on who is the authoritative data assimilator and of that group. Then comes the climate models. Basically, climate models are mathematical representations of the climate, and they kind of segregate or divide the Earth into latitudes and longitudes, but also they divide the Earth in vertically. So we would be having 20 or more than that pressure levels vertically, showing what's happening at different levels of the atmosphere. And at each of these grid boxes, they try to resolve all the physical processes. So basically, there would be a part of the atmosphere, there would be the ocean, and also what's happening in terms of the interactions between land and the ocean. And some of the models, they have biases, like, because the way they are set up or because the way they are run. So it's very important to understand a climate model and a climate model projection, looking in terms of whether it has a hot bias, which is positive, or it has a colder bias or negative bias, and do bias corrections in terms of, that particular variable. So again, whatever, comes out as a projection, we do statistical tests and analysis in order to understand how feasible it could be in the near future or in the far future, rather than just saying, oh, this is it. Because it's a climate model, it's not a psychic prediction. That's what I like to say. It may happen, it may not happen, but we have to understand how close we are to the reality of it being a possible case. And this is an example of the CMIP6, which is the latest generation of global climate model projections. Basically, it shows the different future scenarios. So we have a wide range of scenario coming from the green scenario, which is the most optimistic scenario, where we are saying that we are just going to go renewables 100% from today onwards, and we are mitigating climate change. There's all policies being taken into account, and as a result of which we can limit the temperature change up to 2 degrees Celsius and forcing by 2.6 watts per meter square by 2100, which seems a little bit far-fetched. So there is a middle emission scenario which says, okay, we will have a mix of both. We will have new renewable policies as well, but at the same point of time, we have to take into account of all the damages that we have already done. So that gives us the middle path. And then 585 is the upper range of scenario, which which shows the worst conditions. So, for example, if we do not deploy, and this is going to sound a very anti-renewable scenario, but again, this is just to assess for bankability. So, in the worst case scenario, if the extremes just increased, what is going to happen in that sort of a state? So, SSP 585 is usually to understand all the worst possible cases, both in terms of bankability of a project and also in terms of human settlement. So in case there is this pathway being followed, so what's going to happen to the sea level rise and how it is going to be impacting a whole lot of people, industry, and everybody. So here is the most fossil-fueled development scenario, which is the 585. But something realistically would be in between SSP 2.5 and SSP 370, which are the mid-emission pathways. So I'm just going to give a small concise thing of what I said till now. So basically we saw that there are 4 different types of data types: observational, which are ground stations, and some examples for Australia. We have a Bureau of Meteorology, which has a couple of weather stations which are still under maintenance, which are still recording, and then there are individual meteorological stations set up by different companies, even some research institutes. Then we have reanalysis data, which is data assimilated from all these observations and the ECMWF models. Some examples would be ERA5, MERA2, and BARA, which is the Bureau's data. Then satellite-derived data, which is again a type of observation, but mostly we use something called remotely sensed data. 2 main examples would be Sentinel and Himawari, which actually covers the Australian domain. And then the climate projection data. So we have CMIP6, all the CMIP family from CMIP 3, 5, and 6. And then we have Cortex family. So there is a whole bunch of Cortex generated model data that were downscaled from CMIP 5, and now we have downscaled from CMIP 6. There's NACLIM. So a bunch of modeling group, they provide data to NACLIM. And then there's Queensland climate projections. So they have a huge bunch of data sets. They have a nice dashboard, and a really, really good data if somebody wants to look into Queensland. So for energy projects, we need high temporal resolution data if we are designing a site. But in terms of a longer term investment, we would mostly look into something which has a high spatial as well as a high temporal resolution. So do we have any questions, or else I'll move forward? All good? Okay. Okay. So now I'm just going to touch upon each of these types of data and just talk about what are the different sources which are freely available, and we can just tap into it to use. So for the observations, I think Bureau of Meteorology gives you high resolution data, but you need to purchase the extreme high resolution ones. The monthly ones or daily ones are pretty much free, that you can download it from their website. But then there is another product called Australian Gridded Climate Data. So Australian Gridded Climate Data uses some of the BOM weather stations, and they run their own set of numerical models to give that gridded product, and mostly have rainfall data for the AGCD ones. But we also have another data source called Silo, which I actually found out just because I was preparing for this presentation. So Silo has some really high quality data for temperature, rainfall, pressure, even clouds. And then NOAA, which was being maintained by the US. It's a shame that it's not. They have vast resources of data for different purposes, and they have data from spanning even from minutes to daily and monthly. And some of the data sets, they actually cover Australia as well. So if you're interested to look in the high quality data that was maintained before 2025, I think we can still use NOAA as a really good source. Then for some of the solar data, we use the Baseline Solar Radiation Network, BSRN, which has high quality pyranometers. Even some of the BSRN sites have spectral data, so spectrally resolved irradiance data, along with temperature, rainfall. Some of them also do measure clouds. Then another one is SURFIT. So SURFIT is again only for US and was maintained by the US government, not maintained anymore. And then Aeronet. Aeronet has aerosol data sets spanning across globally. So I have tried to put some figures of the Aeronet stations over here, you can see. They also do measure some irradiance and some other solar products. And then we have the WMO weather stations located at different parts of the world, but they do record mostly temperature and precipitation rather than looking into any solar and wind variables. So when we talk about the data, it also, there's so much data, but again, coming in so many different formats. Some of them are really easy to download with CSV and text files, but some of them could be in a very different format that we need to do some pre-processing. So I've just tried to make some notes of all the major data formats that comes from the observations. So it could be the CSV, text, GeoTIFF. So GeoTIFF would give you the geographical reference and the location of that data. Basically, it contains information about latitude, longitude, altitude, all those sorts of data, all those sorts of information that you have. So a GeoTIFF data is mostly like you can use it for any GIS software. very compatible with that. And then we have ASCII and NetCDF, which there are different data handling tools like Python, R, and MATLAB. They have different packages which handles the specific type of data sets. So for station observation data, it's mostly useful for validation. So we use station observation data as a ground truth for validating the climate models all the time. Then also it's used for validating the performance matrices, the capacity factor, in terms of any sensors that are attached, like the module temperature is measured by if it's getting measured. So we would be using those sorts of data sets. Again, understanding the local microclimate impacts on the plant performance, like changes in the albedo or clouds, how it is impacting the intermittency and ramps. And very important for understanding predictive maintenance of that particular solar or wind farm. Now going to the satellite observations. So again, vast amount of key sources of data. One most important one is NASA Power. And then there is NRL, NSRDB. So NRL, NSRDB basically gives you solar radiation data set, something like this. So this is like compilation of the different satellites that move through, that pass through the different region, and then they produce the entire map like that. So for Australia, they collect the data from Himawari and Sentinel, and basically for different other parts of the world, they have all this different satellite paths going through it, which they have compiled, and they generate the data. Then we have MODIS. MODIS is very important and useful for us when we are trying to understand bushfire hotspots, because it gives very high quality data. The only issue is the resolution. It's a very coarse resolution data spanning up to 0.05 degrees, and sometimes if you go for the level 3 product, which is the global picture of it, it would be only available in daily and not at a more frequent time scales. For NASA Power, it's again, you get higher temporal resolution data. It could span from hourly, but there is a compromise with the spatial one. You get it more in terms of 1 degree. So it's like 100 kilometers cross 100 kilometers. So you're really not understanding what's happening in between 100 and the other point. Himawari and Sentinel, they are excellent sources. So Sentinel gives you up to 10 meters of resolution, high resolution data. I've used Sentinel before, long time before joining my PhD, when I used to work for the Indian Space Research Organization, trying to find out the pools of fish. So we would detect chlorophyll with Sentinel data, and then just the fishery industry would use it to go and do fishing. That was fun. And then types of fishes and all that, all the different type of fish and all that sort of stuff. But the issue with that is it's not very frequent. It comes from 5 to 10 days. That's just because it's giving such a high spatial resolution data that it takes a longer time to come back to the same position once again. So basically, for the satellite observation, where we, so again, there is a bit of limitation for both. If it is a geostationary or a polar orbiting satellite, depending on what type it is, the spatial resolution would vary. And the temporal resolution is, again, an issue. Sometimes it is hourly, but compromised in the spatial resolution like the NASA Power. And for a satellite data, it comes like a raster format. And we can use some GIS tools like ArcGIS and QGIS in order to understand that data. But also Python has a couple of other libraries like Xarray and another one, I think, can't remember on top of my head, but there's another library where we can use to understand this spatial resolution data sets from satellite. Again, some metrics that we can understand from these sorts of satellite data is we can use it for cloud and aerosol detection, understanding the impact on the PV power generation, but also we can use it to understand surface albedo and reflectance, which is a huge thing for BIPV and which is a huge thing for bifacial modules. Again, shading and terrain influence, very important for solar, especially in Europe where people are trying to build in mountainous regions. Gets huge shading because of the mountains. So that's a big issue there. Then for regional generation and forecasting, like Melanie mentioned in her previous talk, that she had some issues with the satellite not able to give it on time, retrieve the data on time to do the forecasting thing. And then solar farm sitting and grid integration. So again, as I mentioned before, huge source of data which we can use for all these different types of aspects, where we need like really high quality spatial resolution data. Then going to reanalysis. So basically, reanalysis combines the weather prediction models and the observations, and also they have their own, and also they gives it gives us data at a high spatial and a temporal resolution. Arrow 5, Mera 2, Barra 2 are the most used commonly data sets in the solar and the wind industry. Arrow 5 can give up to 31 kilometer for resolution spatially, but on the other end, Mera 2 approximately 50, but Barra is really good. They also have some downscale products for different parts of Australia where the resolution can vary from 1.5 kilometers. An easy way to download the Mera 2 data is Renewable Ninja if you're looking for some point based estimations. So you can just go there, give your latitude and longitude, and it spits out not only the data, but also it translates it to solar and wind matrices that you're interested or that they can calculate. But then if you want to have a look more globally, you can go to Copernicus CDS website. So ECMWF CDS website again has a bunch of different data for Arrow 5. So you can either have the surface level data, or you can, if you are interested in looking at what's happening at the different heights of the atmosphere, you can even get that type of data from hourly timescale onwards till monthly. And then the last image over here is the GES disk to download the Mera 2. Mera 2 products are grouped together, so they are radiation products that would be bunched up, grouped together. So basically, you can, if you download that product, you can get your solar radiation, but also long wave, short wave, long wave radiation and temperature. And then they have, I think, the ocean products again clubbed together like that. Just wanted to show you the Barra's resolution. So the outer domain is 12 kilometer, covering the entire Australia, New Zealand and the maritime continent and some parts of India as well. But we have 1.5 kilometer spatial data sets for all the smaller domains over here. And I think there is another version of the data which has up to 10 minutes temporal resolution. So basically all this data is the highest temporal resolution is every hour, but they have another downscale product which gives data at every 10 minutes or 30 minutes of fewer locations across Australia. So some uses, again, to look at the variability, especially in terms of spatial variability before doing a wind farm assessment, wind farm sitting, or understanding which location is more useful for having a wind or a solar farm, understanding extreme weather frequency, and how it is impacting the energy generation. Also a very, very good resource for O&M scheduling and optimization, especially because if we can take advantage of that 1.5 kilometer subgrids, which covers most of the larger scale solar farms and wind farms across Australia. And also excellent source for understanding resilience and for consistent, and gives it's really reliable for energy modeling because it gives you a longer term yield data.
Who's responsible for building
It's Bureau of Meteorology. It's maintained by the Bureau here. Then the climate projections. So as I mentioned before, for the climate projections, basically the Earth is treated as like smaller grids, and every pocket of grid has the physical processes representing what's happening at that pocket or at that location, at that grid square in the Earth. So the global climate scale, global climate models, they have a coarser resolution, typically up to 100 to 250 kilometers, and they can span from hourly to monthly data sets. And basic examples would be CMIP5, CMIP6, and then CMIP5, CMIP6 would have different families of data, different models. Like, for example, AXIS, is one of the models which is a part of the CMIP5 and CMIP6, and then they would run the different scenarios and have different ensemble members in that. Again, the climate data store where we can download ERA5 is a source of downloading the CMIP or the GCMs. But there's also Earth System Grid Federation, which is quite easy to use and download this climate projection data. The only issue with that is it's a huge amount of data. So we really need some sort of high performance computing in order to process all that huge data sets. In terms of tools, so Python library is excellent, but then there is something called Climate Data Operator. So this is very handy, and it allows us to have a quick check and a quick look at the data set just before going and downloading something. And similarly, Panoply, it would help you in just giving that visual picture of that one timestamp or the data that you're interested in before downloading that. And then we have something called regional climate models, just because I mentioned that in the global climate model, the spatial resolution is quite coarse. So we use the global climate model to focus on some specific domain. So, for example, in this figure, we are just focusing on the smallest subsection of the Earth. And then we run it for inner domain and outer domain, which basically gives you a higher spatial resolution climate model data for the future with having the same scenarios, but it needs all the other variables coming in. So basically, it would need parameters going in at the boundaries. So we would have lateral boundary condition and initial boundary condition in order to run these regional climate models. Again, for Australia, NACLIM just released its new generation model called NACLIM 2, which I think has more than 15 climate models at hourly timestamp. But then there are other models as well, which are included in Cordex projections. So Cordex is something similar like CMIP, which has a bunch of different countries participating, running, giving smaller regional climate model data sets for different parts of the world. And very useful for resource assessment, understanding what is the long-term impact of climate change, looking at the extreme generation, and understanding storage and planning and all those sorts of stuff. So I'm just going to give an example of how we assess the confidence level on future projections. So because we are generating such amount of vast data and every model has its own configuration, so we want to understand if what we are seeing in the future is actually relevant or not. So we do t-tests at every grid point, and let's say we have an ensemble of 10 members. So then we would do t-tests on those 10 members at every grid point. And then at every grid point, we are going to see if more than 50% of the models, they are showing any sort of significant change. And if more than 70% of the models, they are agreeing in the direction of the change, then only it is a significant change in the future, and that's likely to occur. But there would be regions of insignificant agreement where at least less than 50% of the models, they are agreeing with the change. And then there are completely disagreement where we are not at all sure what's going to happen in the future are the regions that are patched in white. Basically, these are the regions where at least 50% they are showing that there's going to be a change in the future, but we don't know the direction of the change. So maybe some of the models are saying that it's going to increase, and some models would be saying it's decrease. So that would be the regions of most uncertainty in a climate projection data set. So some of the uses of the climate data to understand in the energy metrics, it would be understanding the future potential of solar and wind for different future scenarios, then impacts of temperature rise on PV efficiency, or understanding degradation rates, physical mechanisms that can impact the degradation of the PV systems. For understanding and planning climate resilient energy systems and technologies which would be performing better in one climate scenario and one part of the world, but might not be performing that good in the other parts of the world. And also very important for scenario-based investment risk assessments, especially for the insurance industry and for the banking sector, and also the bankability of the projects. This is a small overview of all the data sets that I mentioned. Basically, the ones punched, labeled in blue, they are the reanalysis data sets. We have ERA 5, 2 different variations, ERA 5 land, BARA 2, NCEP, NCAR, JRA. So each of them have different spatial resolutions depending on the requirement of, we usually choose our data set like that. Most of them, they have data from 1940 onwards, and some of them from 1980 onwards, like MERA 2. The ones in the white, they are satellite derived or satellite plus model derived data, like NASA Power, MODIS, then Sentinel-3. So MODIS and Sentinel-3, both of them, 2 and 3, they cover Australia, which is again a very high resolution. Then the ones in green at the bottom, these are the ones, the climate model projections, CMIP family, CMIP 5 and CMIP 6. So the spatial resolution varies based on each model run. And before using the CMIP data for certain analysis, we always try to regrid them and have them in the same same resolution, so that it's easy to compare and we are not comparing something, 2 different things in 2 different resolutions. And then the Bureau has also projections, which is called the BARPA. Again, from hourly on, has hourly data from 1960 onwards till the end of the year. And just going to give a small example. So, this morning, Melindy talked about ramps. So I'm just going to give it a small example. So basically we can have clouds coming in during any time of the day, and, which can result in increase or decrease in the irradiance, which results in increase or decrease in the power generation. So up ramp event, or the positive ramp event, which would lead in a jump in the power, and similarly, decrease in the power output is known as negative ramp event. So for the renewable energy industry, if we are looking at ramps, but we are looking at two different separate issues. So in the first one, we are interested in understanding optimizing the generation. So this is a site level data, let's say, and it has a lot of ramps throughout the day, and they are more interested in understanding how we can use storage or integrate storage. So for them, when they're looking at ramps, they really want to have a high temporal resolution data set. So that could span from 1 second up to 1 hour. So ideally something in terms of second to minutes would be the ideal case for this kind of example, looking into ramps and then combining it with the battery and storage. But if it's a new if we are trying to look at a new location to choose where we want to have a new solar farm for this example. So we are more interested in looking at spatially what is happening. So how many ramps we are having spatially per year at different parts of Australia, and what is the duration of these ramps. So in that case, we are not only interested in the higher temporal resolution data, but we are also interested in a higher spatial resolution data, because we want to look at things, what is happening spatially across different parts. So even though it's ramps, which is the same thing, but the industry can look into it in two different ways, because there are two different problems that they want to solve. And again, different data would be useful for this. Just want to quickly go through this because I'm moving a little bit slow. So basically, what Merlin touched upon again in the morning about forecasting and climate projections. So in terms of impacts and in terms of utility of forecasting, we are really interested in what type of scale that event is occurring in. So if you want to look at what's happening in terms of cloud movements and thunderstorms, we would be really, really interested in forecasting it in terms of seconds to up to days, because that's how quickly that things can change in that part. But then when we talk about a more seasonal scale, so we are more interested in what might happen in the next bushfire period or the next heat wave period, whether bushfires are going to be impacting the materials, or how is it impacting the generation side of the thing. And in terms of the climate projections, it's usually from decadal to multi-decadal, very important for site selection and material selection, and also in terms of resource assessment and storage and planning. That's because the events are occurring at that larger time scales. So at last, just want to end up by saying that for the renewable energy industry, there is a huge chunk of data, and the data can be segregated in terms of the data type, the time periods, resolution and time horizon. So it just basically depends on what we are interested in looking at and what we are trying to solve. And at the same point of time, TMY file, we need to move away from the TMY files and need to look at the whole bunch of data, a long range of data, in order to understand the different possible scenarios, or what is happening, or to get a whole bunch of picture of what is happening at that location. And thank you. Can have any questions? And I just wanted to shout out to the funders of this workshop, the DGFI. Which I should have mentioned before, but anyways, never too late.
Do we have any questions? Shukla.
One question. Does all of the data sets has kind of the solar irradiance data and wind speed data included in that?
Yeah, so the data sets that I showed, most of them have wind speed and irradiance data. So Silo, which is a new Australian data set, they have measurements. That was mostly for the agricultural side. So they did not measure irradiance, but they measured temperature and precipitation. But I feel like, again, if the two weather stations are kind of close by, and it's not a huge, or the climate's not huge changing, we can still rely on it rather than using something that is not at all relevant. That's my personal opinion.
Thank you. And I actually have another question. I actually saw in one of your slides that there are some data set is actually forecast until the 2100. Is that like a kind of a forecast into the future?
Yeah. So those are the climate projection data sets. So you can have them in global scale, giving you the entire picture of the Earth, or else some regional climate model projections. So for Australia, we have Codex Australasia. So Codex is a global initiative where all the different countries have come up together to give projections for their country. But also the government, the New South Wales government, I think, is a part of another data set called NACLIM. So it gives you projections for New South Wales, South Australia, and part of Queensland. They also are up till 2100. And then there's Queensland's projections as well. So Queensland government has their own projections. Of course. Okay, if we don't have any questions, then we have some nice cupcakes, some sweet desserts before we start the next hands-on session that's going to be led by Abhi.